Potential energy, or stored is another word for this kind of energy. There's a number of ways we can do this. It's energy that we're not using yet, but we could use it in the future. Gravitational potential energy, chemical potential energy, elastic potential energy, and nuclear energy. I'm guessing that you've got a pretty good idea of what they are. Oh, okay, gravitational potential energy. So, stored in an object when it's above the ground, because we know that if we've got something above the ground, it's sitting there, it has energy, it's not doing anything at the moment, has the potential to do work, and then once we release it, it will fall, gaining kinetic energy on its way down. And when it hits the ground, that's when the work is done. Yes, so not a great example if you're standing below whatever it is, particularly if it's a boulder like this one up on Castle Rock. Or if you're these people in a plane without the parachute, that's not great. But anyway, it doesn't matter. This is called gravitational potential energy when something is high up off the ground. So a mountain, funnily enough, even though it's attached to the ground, has gravitational potential energy. And it is pushing down on the ground. Shouldn't surprise you. The higher something is, and the more massive it is, so the more mass it has, the more gravitational potential energy it has. That makes sense, doesn't it? Think about the work an object can do when it hits the ground if it falls from really high up. Or the work an object can do if it falls from really high up and it weighs a lot, has a lot of mass. G is for gravity. So this amount of potential energy depends on the gravity on the planet or wherever you are. So if there's no gravity, if you're in space, nothing has gravitational potential energy. That makes sense, doesn't it? Chemical potential energy. So this is the energy stored in substances, can be released through chemical reactions. So things like batteries, food, fuel like wood or oil. I think it might be kerosene, not sure. So these are things, but so many other chemical substances have chemical potential energy. Pretty much anything you can burn has chemical potential energy in it. It will be released when you have that chemical reaction of burning it. Doesn't just have to be burnt. There are other ways we can get it out. So, food, well, the sugars are kind of combusted inside you, but without an explosion. That energy is released into your cells to help it do stuff. Elastic potential energy. This one's pretty interesting. So the energy stored in something that is stretched or compressed. So we have a string that is stretched here. We know that nothing is moving yet. There's no kinetic energy. There might be a little bit of heat energy in the spring, but there's no kinetic energy. As soon as we release that, the elastic potential energy turns into kinetic energy. This thing starts moving. We've got a ruler here. I'm sure most of you naughty children have done this. So when you bend a ruler back and you've got, it's kind of like a catapult, you've got something there, you've got elastic potential energy, you release it and it becomes kinetic energy. Not just kinetic energy in the projectile, kinetic energy, this ruler is going to move too, isn't it? We can get elastic potential energy, this is extended, but we can also get it in something that is squashed. So if we've got one of those, so in suspension in a car, we've got these kind of springs that are spread out a little bit. And as you hit things, they compress. If you really go over something bad and you feel as though you bottom out, as in you get a clunky, that's when you've compressed the spring completely. What's going to happen, elastic potential energy is stored in that spring and it's going to go back into its shape. So it's going to lift the car back off the ground. And this is the other way of doing it, by stretching it. Let's have a look at this golf ball. Unbelievable. It's at 10,000 frames a second, so super slow motion. This is the bit that really gets me. So it's got that shape, and then look what happens. Elastic potential energy, turning it into kinetic. Crazy. Bet you never thought that was what it was going to look like. Nuclear energy. It's the energy stored in atoms, and it's released during nuclear fission or nuclear fusion. So nuclear fusion happens in stars. Nuclear fission is when atoms break up. So we've got nuclear fission down here, so this one's breaking up. We have a little neutron, we hit a uranium, and you've heard uranium is radioactive. We add a neutron to this type of uranium, and it becomes unstable. So uranium-236, uranium-235, The 1 comes from this neutron that gets added to it. Uranium-236 is unstable, and what happens is it breaks apart into 2 different elements. When that happens, a lot of energy is released. And also, little neutrons are released too. And they can go and crash into some more uranium-235. If you've heard of a chain reaction in a nuclear reactor where it can get out of control, this is how that can happen. So if we hit 1, these 3 get out, then another 3, another 3, another 3, and nuclear fusion. So we got deuterium and tritium. They're both forms of hydrogen. This is happening in a star. So you've got really strong forces in a star. Gravity in the heart of a star is incredibly powerful, and it can actually shove 2 protons together, 2 heliums together. And what we have when we smash these together is we end up with a helium afterwards and another neutron bounces out. This is an example of something that actually happens. These heliums can then, to do with other forces in a star, can become bigger and bigger and bigger atoms. So all of the atoms that we have in the universe were created in stars and in explosions and in the death of stars. But when this happens, the energy is released during this process. So we get energy released when atoms break apart. We get energy released when atoms squash together. That sounds unusual, doesn't it? Happens both ways, depending on which atoms they are. Energy comes out, and that's the heat and light we get from stars. So sometimes this energy can be quite dangerous to us. We need to be really careful. So people who work at nuclear power plants or people who are scientists who work with radioactive substances need to be very, very careful to do with the amount that they're absorbing, because it can cause cancer and other things. So people who work in hospitals, sometimes they deal with radioactive substances, particularly in a CT scan, I think. Anyway, energy transfer. Energy can be transferred from one object to another object. During energy transfer, the form of energy stays the same. Sometimes energy is wasted. Okay, so this little guy moving, he's going to come in, he's going to make that one move, that one move, that one, all the way across, and eventually this one's going to fling off the end because the energy is transferred through. The one on the end, eventually this is going to stop. It's going to click back and forth, and eventually it's going to run out of puff. Where has that energy gone? It still exists. Energy can be transferred or transformed, but cannot disappear. It always becomes another kind of energy. Imagine this in your head. Imagine this happening. What can you see, or what can you feel, or what can you hear? You can hear noise, can't you? So some of the energy, some of the kinetic energy is becoming sound energy. If you've ever played squash or cricket or a sport where there's impact, you would know that when something keeps getting hit over and over again, it becomes hot, doesn't it? Yeah, or if you're squashing a ball in your hand, you notice it does get hot. So you're turning kinetic energy into heat energy. So there'd be little bits of heat. These would get slightly warmer. This one lasts for a fair amount of time, doesn't it, when it's clicking back and forth. But kinetic energy becoming kinetic energy, and then we've got some wasted energy. This machine is not designed to produce sound or heat. It's designed to continue to be kinetic. So we consider it wasted because that's not what we're going for. There are some transformations there, but we'd still consider them transformations, but we're talking about wasted energy. Here we have energy from the wind transferring to a turbine. Kinetic energy becomes kinetic energy. It's still the same. Then there's a transformation that occurs to become electrical energy. That's a satellite, I think. Pretty cool. Energy transformations, you probably know already what I'm talking about here. So it can be transformed from one form into another. So here we have gravitational potential energy. This girl releases the ball and it now has kinetic energy. When it's halfway up, it has half the gravitational potential energy that it had at the top. And it started off with zero kinetic. Then whatever the energy is that was gravitational potential has now become kinetic. So just say it had 20 joules at the top, halfway down it's going to have 10 joules, the other 10 joules will be kinetic. And we can work out using that kinetic energy equation how fast it's going, as long as we know how much mass it has. That's pretty cool, isn't it? When it gets down to the very bottom, it has no potential energy and it's all kinetic. And then what will happen is that kinetic energy will become other things depending on what the ball is like. If it's a bouncy ball, it might turn into elastic and then come back up and get more gravitational again, etc. So we've got light energy coming in, solar cell will turn it into electrical energy, and then it will become light and heat energy if it gets to a traffic light. We could use it to produce kinetic energy as well if it went to a fan, or lots of different things that you might have in the home, like a blender or a mixer or something like that. Input energy is electrical, output energy is heat. Not much sound coming out of this, but lots of light in a toaster. So we'd consider the sound and light as wasted energy. But heat energy is what we're after. In a toaster, you'd probably consider it's not a very efficient bit of equipment. It's efficient at turning the electrical into heat and light, but how much of that heat ends up in the bread? You take the bread out and it's still hot for ages. Electrical energy into sound, heat and light in a portable device. Elastic potential energy, okay, this is a wind-up toy. It's got a spring in it, and once that spring is released, it will do its thing. So wind-up cars and things like that. I don't really know if they're still a thing. You'd remember more than me. You're a kid much more recently than I was. Chemical energy in a car, so that's the fuel, and we turn that into kinetic energy mainly. That's the useful energy we want. Also, we get sound and heat energy out of it. They're undesirable in a vehicle. We want as much kinetic energy out of it as possible. We want a car to be really efficient. The law of conservation of energy. So, energy cannot be created or destroyed, only transferred or transformed. Can't create it, can't destroy it, only transfer it or transform it. You're probably going to think, but we create energy when we do this, blah, blah, blah. But that energy has probably come from kinetic energy. It's definitely come from some other form of energy. You can't create energy from nothing. Energy can be wasted, but it's never lost. So you can see in this diagram, we've got an amount of energy coming in. Could be chemical. It's probably chemical. Could be electrical. So we've got the useful energy coming out. Kinetic is what we're after, but then we're wasting it as light, sound, and heat. So think of a car. Approximately that much is going to be in kinetic, but then we're wasting a fair bit. They're not very efficient. Petrol motors are terrible.